Hi everyone. So this is a question that may be bothering you. What is actually doing the waving when we talk about an electron wave? However, I found that if you're willing to set aside the fact that the electrons, the elementary particles, are in fact particles, and think of them entirely as fields with that have wave motions associated with them, then a lot of this quantum mechanics is quite a bit easier to understand. However, that really does throw away some elements that are true. So, for example, if I have a double slit and I throw electrons through there, and I throw a bunch, just fire a bunch of electrons, what happens is that I get this pattern of pictures. So initially, there's kind of just this random splay. I don't see any kind of pattern. And then down here, you start to see kind of the standard interference pattern that we'd expect from any kind of wave source, right? So this is the pattern that we're comfortable with if we imagine the electrons as waves. However, in order to get there, we start with little dots of light. And here's the problem. This dot of light here, for example, how does it know to go here instead of here? Right? It's completely random where these particles are going to show up. If I run this experiment again, I'm going to get a different initial pattern. Run it again, I get a different initial pattern. There's an essential randomness here. But it's not completely random because I always get this pattern in the end. The aggregate acts in a way I expect, where the individuals act randomly. How can this work? How does it make sense? And honestly, I don't think anyone really knows. It's one of those questions that have been debated ad nauseum until now. Most physicists are not even willing to talk about it. It's so tiresome because the interesting thing is actually using the quantum mechanics, building stuff, making cool things work. Understanding kind of why it works would be nice to know, but it truly is that, a nice to have. So, when we talk about what is waving, the closest we can come to is to say that the fundamental stuff that is waving is the probability of a particle showing up. So this pattern represents a probability distribution, and each of these elements, or each of these events, in aggregate, display the probability distribution. Just like when you roll dice, most of the time you're going to get 7, right? Sometimes you'll get 12, sometimes you'll get 2, sometimes you'll get 4, but most of the time you get 7. And there's actually a very normal distribution to that, the normal distribution. But that distribution is not present in any single one of those dice throw. It's present in the aggregate, the combination. It's the same thing here. That probability wave is not present in any single one of these particle events, but it is in the aggregate. So that's Born. Born was the person who first came up with this interpretation of the quantum mechanical wave and what it means, and that is fundamentally a probability. Now I want to take that one step further and say that the thing that waves is not really the probability, it's the square root of the probability in a way. And the reason I want to say that is because over various lectures I've mentioned the fact that intensity or power or amplitude is associated with the square of the energy content of whatever it is we're talking about, usually in the context of waves, harmonic motion. So for example, in harmonic motion, the energy associated with a harmonic oscillator is proportional to the square of the amplitude, how far that oscillator is going to go. So the farther it goes, the amount of energy is proportional to the square of that amplitude. Well, if we talk about this, if we talk about quantum mechanical waves and particles, where they are, the same thing happens, is that the wave, the location of that energy, if you want to call the very existence of the particle kind of as its energy, the very existence is proportional to the square of the wave function. And this is helpful to know when we get in some detail about the interference. The interference pattern that we see, remember, is not the simple sum of the amplitudes. I'm sorry, not the simple sum of the energy, but the simple sum of the amplitudes of the wave when we talked about wave interference. In the same way, when we talk about the probability of finding something, it's actually proportional to the square of this wave function. Now, I don't think you need to understand everything I just said there. Just a couple things to remember is that the thing that waves is the probability. The probability is proportional to the square of the wave, and that probability is not captured in any single one event, but captured in the aggregate.